Swayam Prabha. Digital India. Educated India.
Hello all. So welcome to Astrochemistry. This is lecture 26. Now, in the previous lecture, we had started looking at a simplified version of the potential energy surface, and I had told you about how the plot of P versus R, where P is a potential energy of a diatomic molecule and R is its internuclear distance. Okay, right? When we had looked into this, I was explaining to you in the previous class about the various regions, where we have a region which is marked by the presence of its equilibrium geometry, okay, right? Where the potential energy is at a minimum for a specific value of the internuclear distance, okay? And we saw the intuition behind why this happens. This region occurs because this happens to be a nice favorable configuration wherein the attractive forces overcome the repulsive forces between considering various electron nuclear combinations, okay, right? So overall, the attractive forces overcome the repulsive forces to result in a nice stable minimum. Now, as we supply some energy to the molecule, right? As we supply some energy to the molecule, the bond, that is, the bond between any two atoms in a diatomic molecule, that breaks. And initially there may be a steep rise, but very soon what happens is that as R tends to infinity, each atom does not recognize the presence of the other, and they behave as if they are more or less unbound systems. That's why the energy does not change beyond a distance. So that explains why, as R tends to infinity, P tends to 0. So we have looked into the regions A and B, and we are yet to look into this region C, which happens when R tends to 0. That is, when the internuclear distance is very close to 0, then what happens to the potential energy? All right. We shall be, intuitively looking at that feature and some more aspects of electronic states, various electronic states of molecules in this lecture, okay? So let's consider, as R tends to 0, that is in region C, right? In region C, R is tending to 0. That is, what happens is that, you try to squeeze a molecule way beyond its, way below its equilibrium bond length. Now what happens? The nuclear repulsion term, nuclear repulsion, right, predominates. And because of this, as a consequence of this, what happens is that the potential energy raises very steeply, okay, right? So your P, right, P increases very steeply. So much so that, under normal experimental conditions, it would more or less be impossible to get this region, okay, right? Because we're talking about a highly unstable system, right? So under such highly unstable conditions, it may not even be able to perform experiments, okay, right? So for the most part, almost always, almost exclusively, this region C, is only obtained using like mathematical calculations, okay, right? So the nuclear repulsion increases, the P increases steeply, the system becomes exceptionally unstable. All right, so the system becomes exceptionally unstable, and this is page 2. This was 1, 2. This will be page 3, and consequently, what happens is that it is not possible to perform experiments in region C. Okay, right? So we're talking about at very close nuclear distances, right? Yeah, almost always. There may be some exceptions, but more than 99% of the case, this is going to be true. Okay, almost always. So consequently, what happens is that, you know, the shape of the curve in this region is purely obtained on the basis of mathematical modeling. Okay, so shape of the curve obtained from modeling. All right. So this is the simplified feature of a potential energy surface. Okay. Now, what I have not told you, and here's where, you know, a key idea is going to emerge related to various different electronic states and electronic transition. This potential energy surface, right, it corresponds to any one electronic state. Please note this point very carefully. Okay, right? This potential energy surface, right, corresponds to any one electronic state, any one bound electronic state. Don't worry about the phrase bound. Okay, I've used the word here bound. I will explain what the phrase means when we study some quantum chemistry for astrochemistry. Okay, right? So this is just roughly, right, this PES. Okay, right? This PES corresponds to only one electronic state. Okay, and corresponding to each bound state. When I say bound, I'm talking about a system wherein an electron is bound by the influence of a nucleus. Okay, right? That would be one example. Okay, corresponding to each bound electronic state, right? There exists, again, I insist that the phrase bound, right, I haven't clearly explained what it means yet, but don't worry about it. It will not affect our understanding currently. We'll see what it means subsequently. Okay, I have not told what bound means. So please note, I've said I've not told what bound means. Just take the word bound. Okay, so corresponding to each electronic state, there exists, a PES, right? In other words, this PES, it will be clear, if you consider the example of a hydrogen molecule. Okay, right? For example, if we say a hydrogen molecule, let's say, again, we simply take the example of H2, right? Now, you must have learned about the molecular orbitals of H2, correct? Molecular orbitals of H2 in your 11th and 12th class. Even if you don't know much about them, okay, you just know that you write the ground state configuration of H2 in the molecular orbital lingo as sigma 1s2, correct? Now, sigma 1s2 corresponds to an electronic state. Okay, this is one electronic state. We saw that as we excite this molecule of hydrogen by supplying either heat or by supplying some light. Okay, most typically by shining light. Okay, right? When we supply some light, okay, when we shine some light, what happens is that this configuration changes to sigma 1s2, sigma star, sigma 1s1, sigma star. I think we put the star here. Yeah, okay. It becomes sigma star 1s1. Are we good? Now, this is a completely bonded state, and this corresponds to a combination of a bonding state and an anti-bonding state. Okay, right? This is yet another electronic state. Now, just like there is a PES, right? There is a PES correspond. This is called as the ground state. Okay, this is called as the ground electronic state, and this is what is called as an excited electronic state. Okay, right? Now, so PES, is for one molecule corresponding to one electronic state. For example, you can, for example, consider this to be the PES of a ground electronic state. How do I know this? Because in so many molecules, okay, the excited state, right? The excited state stays for long enough, okay, right? That you can experimentally measure the equilibrium value and there will be certain differences. So based on that idea, people got to understand, okay, that, it need not be the case that a PES is unique for all electronic states. So corresponding to each electronic state, there exists a simplified PES, especially for diatomic molecules. Are we good? Of course, it's also true for polyatomic molecules, but because we are only concerned with diatomic molecules and considering a simplified PES, so corresponding to the ground electronic state, we shall be having a PES, and similarly, corresponding to an excited state also, there will be yet another PES, right? And when we have to visualize, okay, right? Visualize an electronic transition, okay? When we have to visualize an electronic transition, we must take into account both the PESs, the potential energy surface of the ground state, as well as the potential energy surface of the excited state. Are we good? Okay. Now, are we clear about this point? That corresponding to each electronic state, there exists a PES. Okay. Of course, I've also used this phrase bound, but don't worry about the meaning of the word bound yet. The precise meaning of the word bound yet. Okay. All right. That said, before we actually study what happens in an excited electronic state, okay, right? And what the PES of an excited electronic state typically will look like, etc., I will tell you one more feature, okay, right? Now, consider the PES of a GS means ground state, okay? By GS, I'm just writing it in shorthand for ground state, okay? The potential energy surface of a ground state diatomic molecule. Right? And of course, I'm only talking about the simplified potential energy surface, right? So don't worry about the other details. Now, I said that this is of course going to be the potential energy, and this is going to be some internuclear distance r. We saw that the shape of the curve is going to be like this, correct? Now, in each of these electronic states, okay. Now, if you recall from your last few lectures, right, where I introduced you to the different types of motion possible. Now, what did we see? I think it was in the tutorials, correct? The energy for the electronic transitions, were they higher or lesser than those corresponding to vibrations and rotations? They were much higher, right? They were much higher, okay? So therefore, then the PES of any electronic state of a diatomic molecule, right? Especially if you consider a ground state, there are going to be several vibrational and rotational levels. Let's say that this is one electronic state. Within this, there are going to be lots of vibrational states, okay? Let's just call this like, mu0, mu1, mu2, mu3, mu4, mu5, not mu, okay? mu0, mu1, mu2, mu3, mu5, etc. So the point to note is that within any PES, right, of a ground state diatomic molecule, there exist many vibrational levels, right? There exist many vibrational energy levels, okay, right? And is it just vibration? It's also rotation, okay? But in this figure, I have only shown the vibration energy levels. What about the rotation energy levels? Well, let me call this page 6, okay? Now, what did we see? We saw that there are going to be many vibrational levels within the electronic state. Of course, shown you the example of a ground state. The same is going to be true for an excited state also, but we'll look into that in a bit, okay? For now, there are going to be existing many vibrational levels. Not just the vibrational levels, but there are also going to be rotational levels, right? So, if we zoom in, okay, right, between the various nu0, nu1, for example, just zooming in between nu0 and nu1. We can call this R naught, R1, etc., etc. All right. So zooming in between nu naught and nu1, let's say this is like nu naught and nu1. There are going to be several rotational energy levels. I'm just going to indicate them with dotted lines here. Okay. So this is going to be, let's say, I've drawn like 4 lines, A, B, C, D, and A could be like R naught, B could be R1, C could be R2, and D could be something like R3. Are we fine? Okay, right? So the key point to note is that between any two vibrational state levels, there are also going to be rotational levels. Now, you may be asking, why I'm never talking about translational energy levels at all? Why am I not even concerned about them? Well, that is because I think I've already kind of answered this question in the last tutorial or lecture, right? It is that the translational energy levels are too closely spaced. Okay, they're exceptionally too closely spaced for us to get any spectral information from them. Okay, so therefore we shall be only predominantly concerned with rotational energy levels and vibrational energy levels, which are going to be part of an electronic state. Okay, so the potential energy surface, right, of any electronic state, it actually includes information about the vibrational state and also the rotational state. Now, having said all this, notice that I still haven't told you one feature. Okay, one thing I've not told you yet. Okay, what I've not told yet is, okay, why should there even be like well-defined spacing? Why should well-defined spacing between the vibrational levels, rotational levels, etc.? Okay, please note this. I haven't yet answered this question at all. I have simply told you that there are going to be multiple vibrational states which are going to be spaced, and between any vibrational states there are going to be rotational states. Of course, there are going to be rotational states between nu4 and nu5, nu3 and nu4, nu2 and nu3 also. Just for the sake of simplicity and to make you understand, I have just indicated the rotational states between nu0 and nu1. Okay, all right. Now, with this understanding, we shall now look into how a typical potential energy surface is going to be, considering an excited state geometry. All right. Now, for that purpose, I will keep that intact. I'll just make this page page 7, a comparison of ground state and excited state PES. Of course, when I say PES, I'm only going to be talking about the simplified PES for diatomic molecules. Okay, right? Excited state PES, a typical, not atypical, but a space typical. Okay, a typical illustration. Sorry for the bad handwriting. This is a space typical illustration. Okay, all right. So I'm going to be, comparing a ground state and excited state PES. Now, it is understood, for the sake of clarity, it is understood that on the y-axis I'm plotting my potential energy, and on the x-axis I'm plotting my R. Okay. So for the sake of ease, I'm not going to be labeling the axis here. I'll tell you why I'm not labeling the axis. But always, please understand that whenever I'm talking about a PES, I'm talking about some energy axis, and I'm talking about typically some distance. Okay, especially for the simplified PES of diatomic molecules, it's going to be a plot of an energy, which is a potential energy, with the internuclear distance. Okay, so I'm not going to be labeling the axis here because I want some space to draw these figures. Okay, right? So, but note that on the y-axis, the parameter that's being plotted is potential energy, and on the x-axis, that is going to be R. okay, which is the internuclear distance. So the shape is going to be something like this. Okay, notice this. Let's say that this is the ground state. Okay, all right, this is the ground state and this is the excited state. Ground state labeled with GS and excited state labeled with ES. Now this is my P. Having drawn this, now I can draw the axis. And this is R. And this point is not 0, 0. I have shifted the origin. Okay, right? This point is no longer 0, 0. Okay, this is not 0, 0. I'll make it clear. Not 0, 0. Okay, in other words, with respect to this plot, there has been some shifting of the origin done because I want to make it convenient. Okay, right? Okay, so this is the GS and this is the excited state. And just like, you have like vibrational states in the ground state, there are going to be vibrational states not to be scaled. Okay, not to be scaled in the excited state also. All right. Now, this is a typical illustration which is going to be holding good in so many cases. Now, so, individually, it's easy to understand the features of GS and ES. Okay, that is the ground state and the excited state. What's happening in the ground state? Well, the same phenomenon, there is a well-defined equilibrium bond length. Okay, well-defined equilibrium bond length. And as we dissociate the bond, the curve, moves asymptotically towards, the zero of potential energy. And, at very close nuclear distances, the potential energy shoots up. Likewise, the same features are also true for an excited state. Okay, are we clear? So we're going to be having one potential energy surface corresponding to each electronic state of a molecule. This is experimentally verified and especially true for bound systems. Okay, and so noting that I have not told you what bound means yet. Okay, and that is not a problem. Okay, so we have this ground state and excited state potential energy surfaces. Okay, now what is the key? Okay, the key is that, let's say, typically this is the ground vibrational state nu naught. Notice this again. I have also not told you why, the ground vibrational state is nu naught. This line, notice this, see carefully, it is this line. Okay, even in the earlier figure, my nu naught is this line. Okay, nu naught is this line. It is not the bottom, it is not the bottom point itself. I've given some space intentionally. Why it is, I will again explain, while I actually teach you vibrational spectroscopy. For now, just take it for granted. Okay, for now, take it for granted. So I have not told you the meaning of bound, and I've also not told you why the nu naught. The nu naught here, okay, right? The nu naught here is not at the bottom. Likewise here also, let's call it dash, to represent an excited state. So this is nu dash 0. Okay, right? This is nu dash 0. So in any case, the ground vibrational state does not correspond to the bottom part, the bottommost part of this curve. Please note this point very carefully, and I have not told you why yet. All right. I have also not told you why, we call these bound states. I have also not told you why there should be well-defined spacings for the rotational and vibrational levels. Okay. All these three things will be clear once we understand some fundamental quantum chemistry. Okay. So let's now, we understand the features of this curve, right? And this curve individually, but taken together, okay? Taken together, well, you notice two features. One is that, let's call this R naught, and let's call this R dash naught, okay? Now, if you notice, I could have easily, drawn this curve exactly on top of this, right? That is, I could have drawn this curve such that R naught could be equal to R dash naught, or I could have also drawn this curve such that my R dash naught is less than R naught. I didn't do either. I intentionally do it in only one way, such that my R dash naught is greater than R naught. Right? I did this intentionally, okay? And not just, okay, right? Please note this point. Now, why should that be done? In other words, why did I shift the excited state curve to the right? Why did ES curve, or I would say, why was ES curve shifted to the right? Now, when I'm giving a typical example, right? When I'm giving a typical example, Why did I shift it to the right and why not to the left? What do you think is the answer? The answer is it's going to be that, yeah, what's it? It is that, what is the physical meaning? What is the physical meaning of shifting this curve to the right? Well, it means that in the excited state potential energy surface, the equilibrium bond length, right, is greater, is higher. In other words, the average distance of the electron, if you consider simply a diatomic system, H2, right, containing only 2 electrons and 2 nuclei, okay, right? It means that the electron nuclear distance is greater. Why should that be the case? Can you just give me a qualitative explanation based on intuition? Well, the answer is that. So the question is, I've already drawn it here, written it here. Why is the electronic state curve shifted to the right, and why is R dash not greater than R naught by default? The answer is, as you excite, like a molecule, as you excite the diatomic molecule, right, the electron nuclear attraction is further lessened. Okay, right? It's further lessened. You're further decreasing the electron nuclear attraction. Okay, and consequently, therefore, which means that the electron, right, the average distance of an electron from the nucleus is going to be higher, which implies, right, your R dash naught is greater than R naught. Are we good? We are good with this, right? Okay. So now we've understood that, in an excited state, typically. Now, when I say typically, this is going to be true for more or less 60 to 70% of the cases, or even 80% of the cases. But there are some instances, there are some very interesting instances where, the shape of the curve doesn't shift too much. The R naught and R dash naught are more or less the same. So, but those cases shall be discussed when we, in particular, discuss some special features of electronic spectroscopy. Okay, right? So currently, we need not worry about them. All right. Now, notice another point. Because the curve is shifted to the right, okay, let's say that, a molecule is in its ground electronic state and ground vibrational state. Now, as the molecule gets excited, and the minute the molecule gets excited, right, notice that it does not reach the ground vibrational state of the excited state. Please note this point very clearly. This is some, mu dash n. Okay, right? Please note this point that note as we excite a molecule from GS to ES, okay, ground state to the excited state, okay, right? The molecule immediately does not reach the ground vibrational state. In the excited state, in the excited electronic state, in excited electronic state. So the minute I say excited electronic state, I'm talking about, the minute I say ES, I'm talking about excited electronic state, right? Now, so what did I explain to you? I was explaining to you that, as we excite a molecule, immediately, what happens is that the transition does not happen from mu naught to mu dash naught. It happens from mu naught to mu dash n, where n is much greater than 0. This is almost always the case. All right? Now, why should this happen? Why should it be that the vibrational state and the excited electronic state not coincide with the ground state? Okay? As an answer to this, we shall be looking to the answer in the next class. Okay? Right? On that note, I shall end this class. And to give you a summary, we kind of looked at the vibrational and rotational states within any potential energy surface, a simplified potential energy surface. And we started comparing the features of an excited state electronic state PES with the ground state PES. Okay. On that note, I'll bid adieu and see you in the next class. Thank you.